noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to today's Explainer. We're going to dive into how some seemingly dense mathematical formulas actually serve as the foundational grammar for describing, well, basically our entire universe. We're talking about everything from the crashing of ocean waves to the completely invisible diffusion of heat, and yeah, even the wildly complex fluctuations of financial markets. Partial differential equations, or PDEs, are literally the ultimate mathematical framework we use for modeling continuous phenomena. So let's just jump right in, because we're going to unpack exactly how this hidden mathematical grammar really works.
Here's our roadmap for today. We'll start with first-order equations and characteristics, then move into classifying second-order PDEs. After that, it's hyperbolic dynamics, focusing on the wave equation, followed by elliptic and parabolic equations. Then we'll hit separation and transform methods, and finally wrap up with energy methods for uniqueness.
All right, let's kick things off with Section 1, First-Order Equations and Characteristics.
To really ground this in reality, let's look at what mathematicians call the Cauchy problem. Just imagine for a second that you need to figure out an entire three-dimensional surface, but literally all you have is a single starting string, like an initial space curve. How on earth do you build the rest of the shape from just that? Well, this is where a truly brilliant technique called the method of characteristics comes in. Instead of trying to tackle the full, intimidating complexity of the PDE all at once, which is basically a nightmare, this method scales it down. It reduces the PDE to a system of ordinary differential equations, or ODEs. It essentially lets mathematicians surf along these very specific geometric lines. We call them characteristic curves that pass right through that initial string. And by writing those curves, you can perfectly map out and build the exact solution surface. It's so cool. But okay, what happens when these equations get highly nonlinear and just massively complex? Enter Sharpet's method. This was developed way back in 1784 by Paul Sharpet, and honestly, it's almost like a mathematical cheat code. It gives us this exact, step-by-step framework to find the complete integral of a general nonlinear first-order PDE. Here's how it goes. First, you construct a compatible auxiliary equation. Then, you apply Lagrange's characteristic system, which generates Sharpet's auxiliary ODEs. And finally, by integrating those much more manageable equations, you can isolate your partial derivatives and actually find the complete solution. It's just a beautifully structured, elegant way to untangle what otherwise looks like an impossible mathematical knot.
Now at this point, you might be wondering, okay, but how do all these abstract surfaces and geometric curves actually connect to the real world we live in? It's a great question. While first-order equations are absolutely foundational, the actual tangible mechanics of our universe are largely governed by the next level of complexity. Which brings us to Section 2, Classifying Second-Order PDEs. So it turns out a totally simple piece of algebra actually acts like a cosmic traffic cop. Just by looking at the discriminant, which we calculate as b squared minus ac, we can neatly classify second-order PDEs into three very distinct realities. Check this out. If the discriminant is greater than 0, the equation is hyperbolic, which means we have two distinct real characteristic roots. If it exactly equals 0, that's parabolic, giving us one repeated root. And if it's less than 0, it's elliptic, which yields complex conjugate roots. This one little algebraic split fundamentally decides how a physical phenomenon is going to behave in the real world. It dictates whether something acts like a ripple echoing across a pond, heat diffusing silently through a solid metal rod, or a physical system locked in perfect static rest.
Let's zoom in on that first one in Section 3, hyperbolic dynamics, wave equation.
Okay, so the wave equation models non-dispersive propagation. Think of things like sound or light traveling. But here's the crazy part. Depending on the spatial dimension you're in, the physical consequences are actually wild. In 3 dimensions, we use Kirchhoff's formula, which integrates purely over a spherical boundary. In plain English, that means if you clap your hands in an empty room, the sound wave passes right over you and then clears out completely. Poof, gone. This behavior is known as Huygens principle. But jump down to 2 dimensions, which is governed by Poisson's formula, and it's a completely different story. Here, the integration happens over a solid disk. So think of a splash on a pond. The wave ripples outward, sure, but it leaves these persistent decaying tails behind it. So yeah, in 2D, Huygens' principle just utterly fails. No clean getaway for the wave.
But what if your wave isn't just a single, isolated event, like a clap or a splash? What if you're dealing with an external force that is continuously driving the wave over time? Mathematicians call this an inhomogeneous problem. Well, this is exactly where Duhamel's principle comes to the rescue. It constructs the solution beautifully by taking all those individual, time-shifted wave responses and superimposing them, basically stacking them all together into one single integral. It essentially takes this continuous driving force and chops it up into an infinite series of tiny, momentary impacts. It's a remarkably clever way to handle continuous forces.
Now, let's switch gears a bit for Section 4, elliptic and parabolic equations.
When it comes to elliptic equations, the Laplace equation is absolutely the gold standard. It models perfect, steady-state equilibrium configurations. We're talking about situations where everything is so perfectly balanced that time literally no longer matters. You could wait a second or millennium, and nothing changes. The solutions to this famous equation are called harmonic functions. And let me tell you, they possess some of the most beautiful regularity properties in all of mathematics. That essentially means they are perfectly smooth, without any sudden jumps or jagged edges everywhere inside their domain.
Now, I want to share a truly profound implication of something called Harnack's inequality. It states that for any non-negative harmonic function, you can bound its maximum value by a constant multiple of its minimum value within a defined closed space. And because of this specific constraint, we get Liouville's theorem. This theorem stunningly proves that any harmonic function that spans all of infinity and has a floor it can't drop below must actually just be a completely flat constant. Think about that for a second. There are absolutely no hills or valleys allowed if the function goes on forever and can't dip below a certain point. It just flattens out entirely.
Next up, we look at parabolic equations. And the classic prototype here is the heat equation. Now, I want you to contrast the hyperbolic wave equation, which has a very strict speed limit, usually denoted by the constant c, with the heat equation's frankly mind-bending infinite propagation speed, literally infinite. If you have a strictly localized spark of heat at time 0, parabolic math dictates that the temperature instantly becomes strictly positive everywhere in the universe at any time greater than 0. Let that sink in. While a wave stubbornly has to wait to travel through space, heat diffusion is mathematically instantaneous across the entire domain.
All right, moving right along to Section 5, separation and transform methods.
Sometimes simple separation of variables into standard ODEs just isn't enough to solve a tough problem. When that happens, mathematicians turn to integral transforms. And honestly, transforms like the continuous Fourier transform are practically mathematical magic tricks. By mapping real spatial variables into a complex spectral domain, the Fourier transform takes impossibly hard spatial derivatives and simply converts them into basic polynomial multiplication. You are literally turning dense, complex differential calculus into high school-level algebra. You solve for the unknown there, and then poof, you magically apply the inverse transform to pull the solution right back into normal physical space. It's such a brilliant workaround.
Which leads us to our final topic, Section 6, Energy Methods for Uniqueness.
So, how do we actually prove a PDE has a unique, reliable solution? Well, mathematicians play a really clever game here. They start by playing devil's advocate, assuming 2 different solutions might exist. Let's call them U1 and U2. Then, they define a difference function W between them. Next, they define a total energy functional for this difference and differentiate it with respect to time using tools like Green's identity to track that exact energy.
If they can mathematically prove that the energy of this difference is strictly zero, well, that guarantees that W is zero absolutely everywhere, which means U1 perfectly equals U2. For the physicists and engineers actually building our world, this is a massive relief. It guarantees that these incredibly complex equations have one and only one reliable physical solution. We aren't just guessing.
When we bring all of this together, we basically get the ultimate cheat sheet mapping how the mathematical universe divides physical phenomena into those three distinct realities we talked about. You've got your hyperbolic waves operating with a finite speed and conserved energy. Then you have your elliptic Laplace equations modeling a steady-state minimum energy situation. And finally, your parabolic heat equations featuring that crazy infinite propagation speed and dissipating energy. Each of these three realities requires a completely different mathematical approach to ensure a well-posed problem, whether you're setting initial values, boundary values, or maybe a mix of both.
Okay, let's do a quick rapid-fire recap of some of the most powerful concepts we've explored today, because these terms really form the indispensable vocabulary for anyone pushing the boundaries of physics and engineering. First, the wavefront set. This tells us exactly how and where singularities propagate through space. Next, the fundamental solution. This shows us the precise mathematical response to a single, infinitely dense point source, which we call the Dirac delta. Then there's the mean value property. This ensures that for steady harmonic functions, the average value on a sphere perfectly equals the value at its center point. And finally, Green's functions. These empower us to solve wildly complex boundary value problems just by integrating over those individual point source responses.
As we wrap up this explainer, I want to leave you with a pretty profound thought to ponder. We've just seen how tracking discriminants, characteristic curves, and energy functionals can so perfectly map our physical reality. Everything from the strict finite speed of sound to the literally instant diffusion of heat. So, how is it that a universe so wildly chaotic, messy, and complex can be so flawlessly and rigorously described by the elegant simplicity of just a few differential equations? Honestly, it's a true testament to the hidden, perfectly structured mathematical grammar of nature itself. Thanks so much for joining me on this deep dive today, and as always, keep questioning the math behind our world.
Like what you shares.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.